good morning everyone, and welcome to my talk on asynchronous programming. I'm Bart de Smet, I'm a developer at Microsoft Corporation in Redmond, where I'm active now working on things like LINQ and reactive extensions, also known as RX. And I have the opportunity here to talk about the whole landscape of asynchrony, which includes RX, but also, task of T, the new async CTP, and all of that stuff. So let's actually dive in right away by taking a look at what asynchrony really is about. So the idea of asynchrony is to have multiple parties in your application, multiple units of execution, really move at independent basis. So for example, if you have some UI thread going on and it's doing processing, and you want to reach out to the network or a web service or do some longer running computation, well, you don't want one party, being the UI thread, being blocked on that operation while it's actually doing stuff. So the word asynchrony actually captures the essence of that. It comes from some Greek origin. It's basically not together with time, meaning that those two parties can evolve separately. Now, often there is some confusion about the whole domain because we have this concurrency monster going on, the multi-core revolution, and people confuse words like concurrency and parallelism as well. So I just have those on the slide here to set the scene a little bit. It happens to be the case that in quite some places those things are blended together. Like for example, you're doing asynchronous computations, you're doing that using the task parallel library, you're introducing some concurrency, so there is some overlap between all that terminology being used together in applications. But the idea of concurrency is that the order in which multiple units of work, multiple tasks, not necessarily related to task of T, are actually executed in some order that's not predetermined. So it could be the one task first and the second one, they could be interleaved, overlapped, all of that stuff. That's really what we mean with concurrency. When we talk about parallelism, more often we talk about true simultaneous execution, like for example you have many cores on your machine that at the same time are doing some computation. So they're all happening at the same time. There's true parallelism, which might be native to the hardware. So we'll focus on the asynchrony aspect, and we'll see the other ones pop around quite often as well. So the observation is that today's programs need to interact with the world quite significantly. Whether it's just something as simple as a human being just moving the mouse, and you don't want to be blocked before the mouse is moved, before you do something, well, you want to have an event handler, and that's a form of asynchrony. Your application is reacting to a particular event that's happening, and those two parties are evolving separately. Like, somebody's moving the mouse, and the CPU is doing something else before that, event actually comes in. So you're not actively blocked on that. Another example is like, receiving some packets no matter where you are on the networking stack. Like, it could be the TCP/IP sockets, where you do begin read, end read kind of thing. But it could also be a web service call, like everything that has to do with I/O to the externals actually wants to deal with asynchrony because you don't want to block, for example, UI. And also I/O is a typical case of asynchrony. So there are a lot of places where asynchrony comes into play, and increasingly so, we see all those terminology things like reactive programming, events, callback, coming back in many places of the framework. So what's actually the big story here? Let's take a look. So first of all, just to drive home the whole statement, we don't want to be blocked. We all know that. We're in a connected world. So you have latency, and you want to basically do useful work while some network request is going. You definitely don't want to have the Snow White effect on the right-hand side where your application is not responsive. So you don't want to block the UI thread, and we all know there are ways of doing that today. For example, in WPF and Silverlight, you have something called the dispatcher, and you can do begin invoke on that to basically post a unit of work to the UI thread. And that's something you typically need to do if you come back from some asynchronous operation. So there's some handshake going on quite often. Now, it's also the case that an increasing number of frameworks only expose asynchronous APIs. Like if you look at Windows Phone 7, Silverlight, there you simply don't have an option to block. If you create a web service proxy for WCF in, for example, Silverlight, well, the only thing you get are the asynchronous operations. You don't get the synchronous ones. So you need to do something there. We also have Ajax and the whole JavaScript space, basically based on asynchrony at its core. So let's do something about that. Now, one question is, if asynchrony is everywhere, why is it that we never had some language support for asynchrony? I will actually show you that in the next version of C# and VB, we're actually adding support for async right inside the language. And that makes a lot of sense if an increasing amount of frameworks are actually doing asynchronous stuff, but all in a different way. So we want to have some unification, just like we did with Dynamic, just like we did with Link, was really unifying different stories that are about, the same domain. So we're doing that with async right now. So just to set the scene a little bit further, it's the case that asynchrony has been around for a long time. Here I just have a screenshot from some Win32 API about asynchronous I/O. So the hardware really has asynchronous operations going on. Like you basically fetch some instruction to get data from disk, and what's really going on is that the processor is not blocked while that I/O is happening. So there is native forms of asynchrony quite often available in the hardware. There are also places where you want to introduce asynchrony yourself, even though it's not supported by a lower level of the system, like doing a computation in the background. Well, you just spawn some thread or something to actually do stuff in the back. Now, what's the programming model? Well, quite honestly, I don't understand the programming model of this thing. It's way too complicated. So over the years, we've sort of exposed more of those abstractions in various frameworks to make it easier for you to leverage whether it's native asynchrony or asynchrony that you just want to introduce yourself. So here's a sample of how that whole I/O completion stuff really surfaces all the way to the .NET framework. Now, there are a couple of defects in this code, which I will elaborate on in just a moment. But the main observation here is that you have this begin read method in .NET 1.0, where you basically pass in a bunch of inputs, and it just happens in true C style that the inputs also are outputs, because I'm passing in a buffer. So I pass in the buffer, the length, and all of that stuff. And then the main thing of the asynchrony is that you have to sort of tease apart your code. You need to say, this thing happens to basically start the read operation, and then you have to pass in some continuation, some callback, that gets executed when the results are ready. So that's actually the thing indicated in blue in that little lambda expression sitting there in the middle. So the callback here uses the lambda expression, as I said. It passes in IAR, which is an iasync result, which is basically a correlation mechanism to sort of correlate the begin with the end. So you can sort of correlate those things back. So you can do the processing of the results. Now, there are a couple of issues here that also indicate quite explicitly that asynchrony is rather tricky in a lot of cases. Like here, I'm just saying like, well, some rule of thumb could be like, if you have an object in .NET and it's an idisposable, just put an using block around it and you don't have lifetime issues. So if you just do that blindly in the face of asynchrony, your code is totally broken in this case. Because what I'm doing is I'm basically using the file stream. The file stream gets disposed ultimately once I leave that block, which is after the begin read, but the begin read immediately completes. So in other words, I've already disposed the file stream and the underlying file system operating system handle before I can even do the callback. The callback will happen later in time. That's the asynchronous part. So things are really a little tricky because, well, the language doesn't really compose with those asynchronous operations very well. I also happen to have forgotten this end read thing. So the way that asynchrony works today in languages is it's based on patterns. So you need to know, well, you need to do a begin read, then you need to do an end read somewhere. And it's also not always clear what the begin and the end sort of do. Where do exceptions come out? What's really the contract here? Like end read in this case returns the number of bytes that were written to the array. It's not as trivial as it always seems. Also, you have those mysterious things like passing in an async state or a state parameter, which today you wouldn't really need anymore because lambda expressions can simply close over the outer scope. So I could just capture some local variable right inside that lambda expression. I don't need that way to sort of pass through some state to my lambda expression. So you see some old cruft, I would say, from the old ages of .NET 1.0 still surfaced in this little abstraction. But so it's really tricky for a number of reasons, as I pointed out. Now, over the years, we created new abstractions. For example, we started with asynchronous methods, which we've seen on the previous slide, where you use callback functions. Later, we said, well, event-based asynchronous patterns might make sense as well, where you basically say, I do an async method call, download async, and then I have an event handler, download completed, where you actually receive the results that come back. Now you get sort of a new jar of problems thrown at you, because in this particular case, say that you can do download async multiple times on an object like a web client, and you have a single event handler for download completed. Well, that thing will fire multiple times every time a download operation succeeds. So how do you correlate the download operation back to the completion message? Because they might arrive out of order. If you don't need to correlate them back because you just want to add them to some list in the UI, it's fine. But if you want to correlate them, it's kind of tricky, because then you need to sort of pass in a little bit of state and sort of match things together. So that's another abstraction. In .NET 2, we also introduced this notion of a background worker, which is really taken asynchrony to a level where it's relatively easy to do those long-running operations and computations, which are not native asynchrony, but just you doing some long-running task like copying a file buffer by buffer or something, or computing pi if you want to do that. It's basically a nice abstraction to do that based on events. And then you sort of see that those domains are closely related. In one case, we use callback functions to signal completion. In the other case, we say, well, let's not just use callbacks, let's actually use events. But events are some fancy way of doing callbacks. So those two domains are really tightly coupled. And we'll actually see with reactive extensions that we do asynchronous programming using events. So let's take a look just at the asynchronous methods that we have available today. Just going here with async C#, little project. It's basically what's on the slides, and I just want to prove a couple of points here. The thing is, if you write this code just using fs.read and pass in a buffer, offset, and count, this code would be totally correct, right? I could say var size equals buff, 0, buff.length. And I could just, safely return from the block here and do a console out or something or whatever. But the thing is that lifetime management here blends very nicely. The using block is delineating, the lifetime. As soon as you do this begin read operation, well, you basically have just screwed up the entire application. It might crash, it might not crash, will just depend on how it feels. It's asynchronous, it doesn't even produce a meaningful result here because we didn't have a time before the main thread actually quit to reach the point of doing a console write line. So let's do a console read over here just to stress this thing a little bit further. If I do console read and keep my application alive, well, you clearly see that something is going wrong. And the thing that's going wrong here is that my imperative control flow of using the using statement doesn't quite work together with that asynchrony. Like in this case, it's basically complaining likely on this line. Let's actually see on which line it happens. Yeah, over here, that it cannot access a closed file. And the reason is that, well, this callback function that you see sitting over here is executing somewhere else after the main thread has already closed the file system handle. So things do not quite work out nicely in this world. Actually, if you would look here at the external code, you would see that we're basically sitting on a completion that's scheduled by the thread pool. So that's actually what's going on here. So it's a little ugly. You can work around it. You can save, the iDisposable. Just make sure that you do, the right exception handling, and make sure at some point you dispose the file stream. But it gets quite tricky quite quickly. So some of the new things that we introduced in .NET 4 as other kinds of abstractions are essential to talk about before we actually go into explaining the new async features in C# and VB. So let's start there with the TPL in .NET 4. Well, you've already seen this slide. That's one of the rationales why we actually introduced the TPL, is to make it easier, or actually to reduce the number of clutter you have to basically write to do those parallel applications. We have nicer abstractions, nicer concurrency primitives available in the TPL. And so that's really what we're doing with TPL in .NET 4. So breaking it down a little bit, the essential notion, and I'm skipping here everything that has to do with p-link, everything that has to do with CDS, which are the coordination data structures, where we have like concurrent collection types and those kind of things. I'm just going to focus on task of T, which is also known as a future. So task of T, think of it as a func of T, but that happens asynchronously. It's just a body of work. In this case, it's indicated with the green comment in the code here. That could be a long-running computation, for example, that ultimately returns a value. And so the thing that I'm doing here is just starting one of those tasks. We also say that tasks are hot, meaning that they're already executing at the point you create them. So you don't have to kick them to basically get them started. Tasks are much cheaper than threads. They basically are not backed by single operating system threads. It's not a one-on-one mapping. We have some pooling mechanism going on called the task pool. Now, the way to work with that is, again, those callbacks are surfacing, but now sort of on another level of abstraction, I would say. So no longer you have that begin-end kind of mix and match thing that you have to do. Now you simply have a task that represents a computation, and in order to basically receive data from the task, you can do a couple of things. Well, you could say on the task, just do .result. Now, .result is a blocking operation. In general, you don't want to do that, unless you've already done some overlapped work, like you started the task over here, you did some other work in the meantime, and you say, I can't absolutely do anything useful without getting the value back from the task. So you might decide to block on the spot there by just calling .result. Don't do that in the UI thread, of course, because there is somebody else who wants to do useful work, like pumping UI messages. In order to receive the data in a non-blocking fashion, you use this thing called continue with. And in the literature, this is known as continuation passing style, where you basically compose programs, where you sequence actions of programs by basically passing them into operations. So for example, the CPS transformation for, say, an addition method that takes in 2 ints, typically an addition method takes in int, int, and returns an int. In CPS style, what you would do is you would say the add method takes in 2 ints and also takes in an action of int that will be called when the result becomes available. So you do something like 3, 4, and then you pass in some lambda that will receive 7 at the point that the addition method has completed the result. So everything in CPS is void returning in essence. So what's going on here is I'm doing continue with. Within the scope of the lambda, I have the x2 parameter. The x2 parameter is basically an alias for x, where you can dot into the result, but also into exceptions and those kind of things. So you can basically get all that information out of it. It's not just the raw value that comes out, it's actually the task that comes out, where you can safely get to the result without blocking, because the continuation has already executed, which means that the result is actually sitting there in the task ready for you to grab it. So continuations are your way to do sequencing. Of course, if you take a look at this now, to write code in this style, in this async style, you need to do continue with, then pass in a whole piece of lambda code, and then in that code you might kick off another asynchronous operation, and then you do continue with again, and you start indenting quite deeply in order to basically write your code. It's not as simple as doing semicolons in C# anymore. So all in all, your application logic is ending up inside out. You have a little piece of work before the asynchronous call, and then you have to go to the unnatural act of taking all the remainder of your code and lifting it into a lambda expression. Now, if you want to do something very similar with, like, say, a while loop around this, well, good luck to you. Like the whole primitives, like, imperative style coding sort of breaks down in conjunction with CPS, unless you go all the way for, creating control flow primitives as library functions, which I won't talk about. So here's an example of really doing some sequencing of operations asynchronously. So I just have a task here that gets some file data, say that it returns a byte array. So this whole thing would be, if I would have a semicolon at the end because I'm going to type some more, the type of report would be a task of byte array. Now the next thing I want to do is, once I get that data, which might be a long-running operation, I don't want to sit and wait for that, I want to sequence some additional piece of work to happen. So I do continue with. I basically don't care here about exceptions. I will just dot into the result. So I say, the file data that becomes available is now available in x.result. So the type of x.result will be byte array, because x is actually a task of byte array. If you have errors, you can do a couple of things. In this case, if there was an exception during the asynchronous computation of get file data, it will get thrown at you when you do the dot result. So it will come out of the property. You can also say continue with some continuation flags to say this expression needs to execute when there is an error. this expression needs to execute when there is a success, when there is a cancellation. So you can basically have different continuations on a task to handle the different cases. Now, if you do that, well, you can already see that your code starts looking even more ugly, because now you have some, var report equals my task, and then you need to do report.continue with some flag that says, in case of an error, do this piece of code. In case of success, do this piece of code, and so on and so on. It's not as nice as a try-catch anymore. You need to basically split up the whole piece of code yourself. But say that analyze now returns a double array. I can, again, continue with, because analyze might take a long time, and I want to do something like summarize. That basically takes in the double array, so the type of y will be a task of double array, and then the summarize method takes in the double array and produces something else. I haven't gone all the way here, but say that summarize returns a string array, then the report would be a task of string array. So let's take a look at just this basic abstraction very primitively to get an idea of how it actually works. So async C#, let's just write some code here. Don't need all of this. So the basic idea is just you have this, task type. We have a non-generic and a generic equivalent. The non-generic one can be used to have like an action. It's sort of the equivalent to action without any parameters. And task of t is really the equivalent to func of t, but asynchronously. So let's do, a task of int. Let's actually go to the factory to create a new one, and then pass in a lambda expression here. And you see there are a number of things you can pass in here. Actually, Ingo Rammer has a session this today, I believe, at the end of the day, talking about TPL in much more detail. So I will skim over cancellation tokens and all those options that you have sitting over here. So let's say that I just do a little func that produces some value, and of course I will fake it. I will just return 42 and say this thing takes a long time. This is not the production code you want to write, of course. You want to have some nice algorithm sitting here. But the thing that I now get is a task of int that basically represents that long-running computation. So on this thing, I can do continue with, which is passing in a continuation, and now it's not as simple anymore as assigning, the 42 to a variable, which was acquired in a synchronous, computation manner, and then just doing, all sorts of imperative-style coding. Now I need to lift everything into continuations. So I need to say something like t prime, which I indicate like this. It's an alias for t. I can do t prime dot, and over here I can look whether there was an exception. I can do a lot of things. And you already see some stuff here showing up as extension methods, which has to do with the new C# stuff I will talk about later. But so essentially here I can do console write line of t underbar dot result. And that's safe to do. We are not blocking here anymore because the continuation only gets executed when the data becomes available, of course. So just to prove that this thing is really live, I can do, while true, console write dot, and do something like thread.sleep of, say, 500 milliseconds. Then now I have a little progress bar that's going, and all of a sudden, that callback will happen to do the console write line of t underbar result. And of course, I would like to stop doing that progress thing, and I could just do a while loop while not completed, all that kind of stuff. But you see that things are happening asynchronously. Like, my main thread can continue doing work while the other thing is basically computing some result. So that's the basic idea. Instead of doing something like having a function, then calling the function and just continuing to write code, you now need to lift things into continue with. So can we do better than that is the question. And the answer sort of was given a couple of years ago already by the F# programming language, where they introduced this feature called async workflows, which is basically language support for asynchronous programming. So you need to squint a little because, of course, it's F# syntax, and not everyone might be familiar to this, but the most important thing is highlighted in orangey colors. So I could write exactly the same code here, taking out all of the orange. Actually, I would have to take out 2 curly braces as well. But now I have a function called process async that takes in an I, and I will be of type int. And now I will do some file operation, in this case some image processing kind of stuff. Now just imagine that there are no orange things appearing in this piece of code. Then the code would read something like file.openRead, then you would do stream.read of num pixels, assign the result to pixels, then do a transform, open write, and then write, the file, or actually the result of doing the transform, which could be just some alpha blending or whatever. I'm writing that to the file. And the result would be that this function is totally blocking. Like given an I, it will complete all the way to the end, and then we can go on to the next file, which is happening at the bottom here in my async demo printing piece of code. I would basically do a transform for the number of images that's specified in num images. So I could have 1,000 of those, and they will execute sequentially. And that's not very nice, because this transform thing might be some long-running piece of execution, and it's totally possible to parallelize, transforming pictures at the same time. So with C# you can, or F# better, you can just lift this whole thing into async, and you can say let bang, do bang, and pass in async as another method name. So in this case, I'm saying let bang pixels equals stream.async read. Now the thing what's happening here at this point is basically the compiler is doing a transformation for me that basically turns it behind the scenes in something that looks like this. It basically says, well, I have a call site where I need to assign the result of some method call to something using the let bang construct. And that bang means please reform or reshape the whole code into continuation passing style. So the thing that's happening is that everything that's sitting behind my let bang piece of code on the second line of the async block gets lifted into a lambda expression. And so the lambda expression is this pixels goes to thing. Actually, it needs to be fun pixels goes to. I missed the keyword here. But it's exactly the same syntax as in C# in some sense, where you would use the fat arrow using equals larger than. But so you see all of that code that follows my let bang assignment now gets actually lifted into a function that's scheduled as the continuation to my read operation. So the way this actually works is that based on the block in this case has async in front of it, the F# compiler starts talking to some library that basically can accept all of those little continuation lambdas and do the right thing with them. So all the compiler really does is transforming your code, which typically you have to do manually by lifting all the things into callbacks, like if you go from read to begin read, you need to take all the code and put it in the callback function. All of that logic is done by the compiler for you. And so that's really what's going on here. Now I can do something like async.run synchronously of async parallel tasks, which really means that I'm now scheduling all of those process async things in parallel. So if I have 1,000 images, those 1,000 images are processed at the same time in overlapped manner. And that's all happening without blocking on any operations. It's basically based on continuations that get executed as soon as the file is read or written. So basically, this whole feature in F# sort of shows that we can get out of the mess of doing this manual transformation. It's more general than that, and I don't want to say too much about that, but you've seen it has something like async curly brace a piece of code. You can have other keywords over there as well. It's basically a little bit of extensible syntax. So you can have some other keywords sitting there, and then the F# compiler will just emit code that talks to some builder object that gets all those little lambda functions. And so you can basically intercept all of the control flow and do some useful processing with that. In fact, this is based on a theory that's pretty dear to my heart. It's the theory of monads, which LINQ is also based on. I actually have a talk about LINQ later today, where I will actually show a little bit of monadic computation. But that's a very beautiful thing where you can sort of have control over a lot of things. So F# really has generalized that. And the idea is, the way to think about it is that we have overloadable meaning for keywords. So like this let bang thing basically causes a handshake between the code that the user has written and some code that lives behind an async builder object that's related to this piece of syntax, which could be implemented in your library. So basically you can overload the meaning to let bang. In this case it will mean, well, do the read operation and then schedule the rest as a continuation, but you can do different things there as well, thanks to the general feature. So really the essence for async is this. Like, if there's one thing to remember, it looks a little funky because it's based on, some type syntax, F# syntax. But those are the signatures of synchronous operations versus asynchronous operations at a fundamental level. And you can recognize begin, read, and here as well. In a synchronous method, you take in an A and produce a B, right? And before that B is computed, you don't return. The whole thing is blocked till the computation is done. In the asynchronous world, you always need to have those kind of callback mechanisms, whether it's through events, whether it's through a lambda expression that you pass in, and that's the thing that's indicated in orange here. An asynchronous operation would have as a signature something that takes in an A, as well as a continuation, a callback function that takes in the result of the computation and goes to unit, meaning that's the same as void. So begin read is exactly this. Begin read would be, A would be the byte buffer array, and then, the B goes to unit would be your callback function that receives the number of bytes that were read from the file. In C# style, the signature looks like action of T, and also passing in an action of R, which is the callback. And so the core concept, as I showed in F#, is this async block, and as soon as you put the async block around a piece of code and you use let bang, do bang, and use bang instead of let, do, and use, which are some keywords in F#, you actually end up executing things asynchronously without really messing too much with your code. And this, signature that I have there, it's actually an out-of-order arrival in my slides here, apparently. The continue with signature looks exactly like this. Well, not completely, because there is some task of B around that B, but that's not too material to talk about too much. So let's take a look at async workflows in F#. The sample I have here is basically just a website crawler or a website fetcher using the async feature. So the thing I'm doing here is I'm creating a web request to a particular URI, and this function here, this is really a function definition, is a function called HTTP, that's the name, and it takes in the URL. And actually, if I hover over that thing, it would say that the URL is of type string, if everything goes according to plan, yes. So the URL is a string. It infers that basically by looking at web request.create and all of that stuff. I won't talk about the type inference of F#, which is very powerful. But so I'm doing web request.create, and then I want to get the response out of the web request. And typically I would do something like, use, which is the same as the using keyword. I would say something like use response equals request.getResponse. Well, unfortunately, that's a blocking operation. At this point, my thread cannot do anything before, the response arrives. So I really introduced some blocking here. Notice that I'm doing a using, and the using actually extends all the way to the bottom of the function here. Or actually at the point where the variable is not needed anymore. I'm doing this using just as I did in C#, and it would be safe to do so if I would do things synchronously, because I will actually complete the whole thing in one go. Now, in F# you can basically say use bang of async get response. And the async get response, as you can see at the signature there, doesn't just return a web response, but it returns an async of web response, which is pretty similar to task of T in the TPL. F# has some different abstractions there. But as soon as I get this, I can do use bang, which means that at this point my thread is free to do other stuff. It's only when the response becomes available that the remainder of the code, which is this piece of code, everything beyond the let or the use bang in this case, gets executed. So really what's going on, if I now call this HTTP function multiple times for different websites, the different web requests are actually in flight simultaneously by just doing this little piece of syntactical transformation. I insert async, insert bang, and I put the async block around it. And so now I can do something like get the HTML of all those websites. This is basically just a list of websites. That's a list of strings that would come out of here. And now I do async parallel for each of the sites, basically compute HTTP of site. Now, one thing to notice is that the HTTP function, although it's an asynchronous function, it returns still, the value of the computation. You don't have to pass in some callback that says, as soon as the request is done, here are the results. The result of that function is an async of string. In C# terms, that would be a function from string to task of string, which basically means it's something going on behind the scenes, and you can receive the data by doing a continue with. So I got this async.parallel here. For every website I'm doing that. And async.parallel basically takes in an array of those asynchronous operations, runs all of them in parallel, and only returns as soon as all of them have completed. So, and that's the thing I'm doing here, run synchronously, waiting for all of them to complete. That would be the same as doing wait any and wait all kind of mechanisms on wait handle. And finally, I'm just iterating over the sequence. So the thing going on here is really that the websites are being fetched simultaneously. And you see, well, the websites are coming out quite nicely. And if I would actually install something like Fiddler, you would see that, you know, the 4 web service requests are totally overlapped in time, just by inserting this little piece of syntax here. So that's a pretty nifty feature. You didn't have to throw over your entire code in order to make this work. Behind the scenes, the whole transformation is actually going on. So the good news is that this is not only an F# feature anymore. We're bringing this whole thing now also to C# and VB in some next version. We actually announced this at PDC last year. So let's actually walk through that and take a look at how it actually works. So what I have here, you can already spot 2 new keywords in C#, and that are the only 2 keywords related to this feature that are being added. We have a keyword called async, which you can see over here. It's a modifier on methods that basically says this method completes asynchronously. Means that it's spawning some work that's going on behind the scenes, and it sort of returns prematurely. An async method can return either void, task, or task of T. So in this case, it's an async void. In this case, it's an async task. So let's take a look at process feed async now. So process feed async says, I want to return a task. That basically means I'm going to return an object that represents the completion of the operation. You can do continue with on the task. You're not blocked on the task. Basically, it's something that will notify you at the point the operation completes. And so process feed async takes in a URL. And the thing I want to do here is I want to download the feed, but I want to do it asynchronously. So the new pattern for naming will be, if you have a synchronous method called bar, in the future you will get a bar async method as well. The old bar method returns, for example, an int. The new bar async method will return a task of int. That's basically the way that things are being straightened out. So for example, begin read would have a read async method that returns, you know, a task of int, which is the number of bytes read, which is just the same signature as the synchronous read method. So download feed async takes in a URL, and this thing, if I would actually hover over the var keyword here, well, basically download feed async, given a URL, will return a, say for example, well, I don't really know what the type would be, but say the download feed would return, you know, an X element, which contains the XML of the feed. In this case, you know, download feed async would return a task of X element, which is the task that represents the computation. Now the nice thing is, once you do an await operation on that, which is the second new keyword, the thing that comes out on the left is basically just the value that's sitting in the task. So it's sort of the same as doing .result, but non-blocking. You don't block here. So the thing that happens, I will just show that in just a moment in the animations, is that at this point, you know, as soon as we reach the await point, we have some task that represents the computation. The compiler just takes all the remainder of the code and lifts it into a continue with call, meaning that the whole code is still non-blocking and asynchronous. So let's take a look at how this executes. What I really want to do here is I want to download 2 feeds at the same time. So I want to do process feed async for Acme and XYZ News. So I have some UI thread with a message pump, and it's very important not to block that thing for too long of a time, because otherwise the UI is not responsive. And so the way this thing is going to execute, I will start at the top. I want to call doWork async. So doWork async starts by executing process feed async of acme.com/RSS. It's doing some work on the UI thread. So assume this thing is called on the UI thread. You know, we're doing some work. You know, the white time on the UI thread will be time that we're not doing work ourselves, that somebody else can schedule work on the UI thread. So I'm doing this process feed async. Now, the result of process feed async will be a task object. I'm indicating that with the little boxes on top of it. That's basically a task that represents the completion of process feed async. So that's like, you know, the thing you can knock on the door and say, are you already done? Or, dear task, I want to schedule a continuation to execute when you're done, all that kind of stuff. So what happens now is we actually call into process feed async, and we hit a point in here where we do download feed async. So this code is executing, still on the UI thread, we're calling process feed async. And we hit download feed async, which is not on the slide. Assume it's some BCL code that spawns like a worker or just uses some native concurrency or native asynchrony in the operating system to start a web service request and then ultimately have a completion port to get the results back. So I'm doing the download feed async, which by itself also corresponds to a task. There will be a task object that represents this computation, this ongoing computation. It will not really be assigned anywhere because I'm awaiting it immediately, but there is some object allocated on the heap that represents the completion of download feed async for that given URL. So this will actually be a task that sort of knows about acme.com/RSS somewhere deep in its logic. Ultimately, now what's happening is, notice the little animation here, I'm coloring the var t1 assignment in doWork async. Because we hit an await keyword, we immediately return to the caller. Like this method, the process feed async method, doesn't even continue executing at this point. It says, I've hit an await keyword that hasn't been completed synchronously yet. It's really going in the background. Let me bail out here. I will just remember of the rest of the computation that I need to do in the future when the data becomes available, which will be parse feed into doc and save doc async and all of that stuff. I will remember about that, but I will go back to my caller to say, I've started, and now there's a task T1 that represents this thing that's in flight. And you can always knock on the door of T1 to say, are you done yet? If you really want to do that, you can ask, T1.is completed. But this thing is going at this point. Now, what's the UI thread going to do? Well, it has already returned from the first statement on the first line. It's going to do exactly the same thing for the second line. So the second line we call process feed async. We hit the download feed async inside that method. The method says, well, I've started the download, but it's not done yet. Let me just bail out of here. And now we have a T2 that represents that download feed async that's in flight. Now at this point, we hit the next piece of code in doWork async. The feeds have not arrived yet. They will arrive in the future. Just swap that out of your mind. We're just continuing to execute doWork async, where we hit a new method called task.whenAll, which basically says, I only want to continue if I get the results of both those tasks passed into the method. So that's just the same like wait handle.waitAll. It's the same as wait for multiple objects EX in Win32. The same thing, but on a much higher level of abstraction. So I'm doing a whenAll. The whenAll by itself creates a new task that represents the completion of the two other tasks. So now I have a new task object sitting there somewhere in the heap that represents the completion of that thing. I'm hitting an await keyword, and at this point, doWork async is basically done. It will return to its caller, which might be some button click handler or whatever, and the thing is going. Display message hasn't executed yet because display message will only execute when both tasks have been completed. So now somewhere in the future, whoops, one of those tasks is completed. In this case, it's T2 that's completed. So that's the xyznews.com download has completed. And what happens now is that we get scheduled back to execute the continuation of the download feed async for XYZ News. So code inside process feed async now starts running again. That thing was sort of paused, suspended. Now the data becomes available and it starts ticking again till the next async await point, where it sort of can yield control. So what's happened is we got the text, we did parse feed into doc, which is a synchronous call. If that thing would be utterly expensive, you could have a parse feed into doc async that returns a task and do an await on that thing as well. And that will also go, in the background and whatever. But ultimately here we hit some method called saveDoc async, which we await for, and that will basically be something that takes the document, flushes it to disk, and will signal you when it's done doing so. So this is like, begin write in a file stream. So at this point, we are blocked again, but we will yield control so that we can do other useful stuff. Somebody is taking care of saving the thing to disk. So now we have a new task that represents saving that particular document to disk. That's sitting there somewhere, and we're awaiting that task before we will actually execute the process log.write entry code on the slide. Now the same thing could actually happen to the acme.com, but assume that acme.com takes a long time to execute, it might be that, this write entry call executes before that. So there is some wait time between doing save.doc async and doing the write entry call, because, well, save.doc async might take a long time, and in the meantime, we could have done some UI rendering. But ultimately, we get called back saying, like, the save.doc async for XYZ news has completed, so, you can do some useful stuff again, which will be the write entry part. Now, somewhere in the future, exactly the same thing is actually happening to the acme.com download. At some point, we got called back saying, well, hey, we got the feed being downloaded from the internet. We did all the save.doc async. Ultimately, we did the process log.write entry for acme.com as well. Now, at this point, both T1 and T2 are completed. What happens now is that the task that represents the completion of both T1 and T2, which was allocated over here when we did task.whenAll, that thing completes as well. And now its continuation, which is the code just beyond the await keyword, starts executing. So now at this point, display message done executes. And this could render something to the UI saying, okay, we're done. But in the meantime, you didn't block your UI. All the white zones on this particular representation of a thread could actually do useful UI pumping stuff. So that's basically how the await feature works. So let's take a look at the async CTP to illustrate this. So async C#. The thing I could do here, like as an example, instead of doing continue with, just to set the scene very briefly, if I have a task of int, the real good way to actually get to the result is not by calling .result, because, as I said before, that's a blocking call. You need to do a continue with. And as you see, this whole code now gets transformed. Now, in the next version of C#, you can actually do the following. This code can totally be transformed into the following. You can say await t, assign that to a variable x, and the type of x will be an int32. So that's what you're seeing happening here. So you don't no longer get a task back, you actually get the result out of it. What also happens is if the task actually failed, when the await completes, it will actually throw an exception. So the await keyword can throw the exception that happened in the back when the task was executing, which also means I can put try-catch blocks around this. Like, I don't need to do .continue with in case of an exception, do something else, or do like an if check on the .exception object of the task. I can simply wrap this whole awaiting in a try-catch block if I want to do so. And it will just come out nicely with the original call stack preserved. So assume I'm not doing that, I can do var x equals await of t. I just get the int32 back or an exception thrown at me in case something went wrong. And I can do console write line of x. This is really pretty much the same code as this code, where I don't have to dot into the result anymore, but you don't longer have those funky looking continuations that you need to pass in yourself. Now, my while true thing isn't really worth anything anymore at this point, because, well, this code won't execute till the await actually completes. And in fact, I don't even need those, dotting things, because my thread is totally free. It's not sort of waiting for some result to come back. Like, say that you're on the UI thread, you could just do other useful work. That was just illustrating that things are happening asynchronously. Now, the thing that's going on here is there is a little bit of a red squiggly that says you cannot use the await operator unless your method itself is declared as being async. So you basically need to communicate your intent on the signature of the containing method to say that the method itself is async. So I will say async void main. Now, it's not a pretty good idea to do that with the main method. Typically, you will have those async methods deep inside some UI code, for example. But you could totally do that, and the compiler is fine with that right now. If you do an async method that doesn't contain awaits, you will get a warning that says, like, this thing doesn't really contain any awaits. The code will run synchronously anyway. Why do you ask me to do something asynchronously here? So those two things go together. And by the way, you can also put the async modifier on lambda expressions. Now, instead of just staring at this task of inting, let's show something real. Because this is too simple. I've already shown the demo in a previous talk this week. But let's just focus on one little thing of the Netflix demo over here. So this is a UI application that basically goes to the Netflix movie service to basically download descriptions of a lot of movies, including pictures and whatnot. And one of the things it does is load movies by year. So actually, if I execute this thing and I enter a year and click search, ultimately my code enters the load movies given the year that the user actually entered. Now, I have 3 versions of this thing. The first version is based on synchronous calls. So the thing we're doing here, ignore the cancellation token part. Really, the thing that's going on here is I'm doing some while true loop, and in there I'm doing, query movies. And this query movies thing, if I go into it, takes in a year, a first, and a count, to sort of query movies for a particular range, and we get a movie array back. And the way that works by itself is by doing something like web client download string, which is a synchronous method call. So this will be blocking till the data comes back, and then we'll actually get the movies which we parse out through some link to XML. So this is very synchronous code. We do query movies that corresponds to a single download string, which is blocking for a long time. Well, we could really go to the Netflix service multiple times simultaneously, as opposed to doing all of this thing synchronously. So here I have the code you would actually have to write without the new await features to make this code asynchronous. Your whole control flow is essentially gone. The thing you need to do here is you need to start building some kind of ugly state machine. Maybe you've gone through the pain. If you haven't, it's an interesting exercise. But what I want to do here is I have a while loop and I have a try catch, and all of that stuff, doesn't compose anymore with those callback functions, all those lambda expressions that need to be passed in. So the way this code now executes is by, having an action that takes in a movie array and an exception and does some fancy stuff with that. That's basically the completion of an asynchronous operation will receive the movie array and the exception in case there was an exception. So this is really the code that will execute at the end that I've sort of prepared here. I need to cook up this little lambda expression to be ready to pass in later on. And so if you look a little further, what I'm doing now is I'm doing query movies async, and the thing I'm passing into queries movie async is still the year, the number of images, and the page size, as well as the callback. Just like begin, read, end read, those kind of things, I need to pass in the callback that will get executed when that query movies async is done. And that action is exactly this whole lambda expression I have created here. So this is the code that gets executed when it's done. The reason that my call to query movies async appears inside that callback itself is because I want to mimic this while loop. Like, all the control flow is gone when you do asynchronous stuff. You need to take care of it yourself. You want to say, like, I want to download, one movie asynchronously, and then when that thing is complete, I want to move to the next one, for example. If you want to do something like that, well, you have to wire all of that logic to your callbacks. Like in the callback, you need to say, do I still have work to do? And if so, I will start scheduling it. And, it gets quite tricky quite quickly. So that's actually what's going on here. My code doesn't look at all like the original code. Also the same for query movies async. The method that actually goes to the web client, ultimately I want to call web client.download. Where am I using the client? Oh, okay. I'm using the event-based pattern in this case to basically do an asynchronous web call. So the thing I'm doing is I have a web client, I hook up an event handler to download string completed, and in that code I will have all the stuff that basically executes as soon as the movie has been downloaded. Or the description of the movie. And all of that code now lives in an event handler, and ultimately, again, you see the thing is upside down, right? Like, the first thing you need to do is write up the code that needs to happen when the thing is done, and then you need to kick off the operation, which happens over here, download string async, which ultimately will call that event handler when it's done. So, a lot of plumbing to make this thing asynchronous. Now, if you look over here, with the new async await feature, it looks much nicer. Let's actually contrast the two with each other. This is the original synchronous code. This is the new asynchronous code. Like, not much change, right? The first thing that changed is we introduced the async keyword on the method. And now inside the method, we can do await operations. So instead of doing query movies, which is a synchronous thing, I'm now doing query movies async. The thing you're seeing here is there's some little message on the synchronous one that we wanted to update the UI thread over here, but it didn't quite work because we were blocked and doing other stuff in the meantime. So, so that's the only difference you're seeing there. But if I would actually take out this piece of code, you would see that those two methods really look the same. The only difference is we have an await keyword there and an async keyword there. And now the whole piece of code is running asynchronously, and I can still use all of my control flow. I can use while loops, I can use try catch, I can do ifs, all of that stuff without having to spread out your logic between the main code and the callback code. So let's actually execute this thing just for 2010. That's the asynchronous one, I hope, that I'm executing here. Okay, I don't think it's the asynchronous one. Let me see what the default is. Okay, it's the synchronous one. So it's already not looking promising, right? I can't drag and drop my window. This is the synchronous piece of code executing. So it's downloading all the movies, and when that thing is done, the UI will come up again, and you will see all the movies appear on the screen. This might take a couple of minutes to actually complete. Likely 2010 had a lot of movies. Now, I don't know much about that, but likely that's what's going on. So let's now set the async await, the async await project as the starter project. And actually execute this thing. If I do 2010 search, you see, well, I can update my UI and things are coming in, just piecemeal. As soon as data is arrived, my UI gets updated. Let's actually just set a breakpoint for fun and giggles somewhere in this code. Let's say, display movies over here. Am I in the asynchronous one? Yes, definitely, because there is an async keyword. I can set a breakpoint in there, do a search, and oops, there we go. So what's going on here, if you take a look at the external code, is that the code that happens after the await doesn't look anymore like it's the original code of load movies async. Like we've already left the load movies async method at this point. All the rest of the code beyond the await keyword has actually been lifted into a little continuation, a little lambda expression that's executing on the thread pool upon completion, or the task pool, upon completion of this piece of code. And so you actually see that this is system code that ultimately will sit somewhere high up on the UI thread, presentation framework.dll run dispatcher. That's actually the UI thread. So that's the thing that's really going on. And I could also take a look at, if I can find where that sits, the parallel tasks to basically show you that there are tasks going on here. Oh, this one doesn't use tasks. Okay, but that's fine. Depends, we can do await over anything. This actually brings up a pretty good other point. The await keyword is totally extensible. Like await can be done on tasks, await can also be done on custom objects. You can do an await over any object as soon as it implements a certain pattern. And that's the so-called awaiter pattern. So that's actually interesting to know as well. And I will actually show you that with the reactive extensions, we implement await on observable collections, or observable sequences better. So await is not just tied to task of T. So pretty simple transform that you have to do in your code, just to go back to this slide for one moment. The synchronous code of this whole thing would look exactly the same modulo the async and the await stuff, and the async, suffix on methods, which is just a convention. Other than that, the code would look, totally the same, but this thing is non-blocking, so this is much preferred if you do things like web service calls. So now you can do things like, in your button event handler, you can say, well, my button event handler, let's declare that thing async, then do something like web client.download string async, put an await in front of that, and then just update your UI code right underneath it. There's also a handshake with a synchronization context happening, so that you don't have to do this.begin invoke or dispatcher.begin invoke to go back to the UI thread. It's all taken care of for you. So now you can basically go to web services, for example, asynchronously, safely from your UI code. So the async stuff helps a lot with single value computations. So think about it this way. Say that you go to a file, you want to get a byte array back. That's a single read operation that you're doing to a file, and it's single valued, or it could come back with an exception. So that's a way to get access to single pieces of data asynchronously. However, there are also other stories where you actually have to deal with event streams. And event streams are basically asynchronous computations of multiple values. And that's actually where the technology called reactive extensions comes in, which you can download, and I will actually show you a couple of things of it today. So if you take a look around you, you have a lot of events, not just UI events happening, but for example, if you look at the whole social media space, like things like Twitter, or more recently, the Belgian students created this little project for the Students Do Business Day called Yelper. Those things basically tell you when things have changed. So maybe you want to react to that if you create some application that wants to aggregate those results and do a lot of logic on top of those events coming into your application. You want to start composing events. A lot of other examples here, like stock ticker data. Well, you don't want to sit and wait there before the stock data comes to you. You just want to say, dear NASDAQ, if there is some update to the stock for that particular company, please call me back on some callback on some event handler saying that something has changed. Now, that works very well in isolation if you just have a single event, but now if you have multiple events and you want to do rich composition over all of those things, you need to have some new abstraction, because otherwise you're writing damn ugly code again inside your event handlers, and things look very, very nasty. So how do we deal with event sources in an asynchronous manner? So that's where Rx comes in. Rx is basically this library that allows you to compose asynchronous and more specifically event-based programs using an abstraction called observable sequences. So the whole idea of doing event-based systems today is totally based on a single abstraction. That's just an event handler. And if you want to do something on, inside the event handler, you better know how to write some ugly imperative code. Let me just give you an example. Say that you have a text box, and a text box produces, obviously, text. Now, it has some event called text changed. But, the text changed event, if you actually look at the signature of that thing, it has an object sender and it has an event RxE. Where's the text that has changed? Like, it's not in there. You need to start writing imperative code to go back to your text box, which is basically casting the sender to a text box and then doing .text on that, and then you get your, string back. Now, that's a lot of, a little bit of plumbing you need to do there just to get to the data. Wouldn't it be nice that you can say something like, I have an event source. Now, I want to do a .select on the event source to project those event args into strings. And now I end up with an event source of strings. So I can do transformations on the data that actually comes out of the sequence. And we'll actually see a couple of samples of that. It's also about compositionality, meaning that if you have two event sources and you want to do something with them in conjunction, you can do that pretty easily. And so I just put a little piece of mathematics here. The basic idea here is if you want to compose two sources, f and g, today you really need to insert very fat parentheses on the right-hand side with lots of imperative code and lots of state maintenance to make that happen. In Rx, it's really like dotting things together using a Fluent API. Let me give an example of composing two event sources as well. Oops, a little too quick. Composing two event sources. Think of the following. Say that you have two streams of data coming into your system. Say you have stock tickers from one exchange and stock tickers from another exchange. How do you want to merge those results together and still be able to unsubscribe from those event sources? Let's walk through the exercise. Say that you have one thing called stock changed on exchange 1, and you have stocks changed on exchange 2. Their signatures might be different. The event args in one case might be the NASDAQ event args, and in the other case it might be something totally else. So they're already different there. You need to do some transformation. So how are you going to write one piece of custom logic at the end of the pipeline that handles messages coming from both? Well, you will have to hook up two event handlers to both of them, do some transformation, and forward messages to that custom logic. Well, that might still work, but then how do you want to deal with unsubscribing the event handlers? Like now you've subscribed to two of those, you have a single object that represents listening to both of those. How do you basically tell that object to unsubscribe from the original sources? You need to build a lot of state maps in there. Like you need to say, my new event handler that has been registered gave rise to two event handlers to the underlying exchanges. You need to keep all of that state around to basically be able to unsubscribe. So it doesn't compose very nicely, and I will show that just in a moment. Now, Rx can be downloaded for a lot of platforms, as you can see. .NET 3.5 SP1 and 4, Silverlight 3.4, and more recently 5. We'll actually have the update online by the end of the day on the MSDN Data Developer Center. It's also the case that Rx is built into the Windows Phone. So actually in the ROM of the device we have the reactive extensions built in, which is pretty exciting to have my code in my pocket all the time. And we also happen to have a JavaScript version available where you can actually do things like Ajax using Rx. So let's take a look. The basic idea of an observable sequence is this. There are only two ways that your application can get to a sequence of data. One case is where your application talks to the environment by saying, please give me the next value of a sequence. Typical sample, SQL data reader. You're saying, dear SQL data reader, move to the next element. And you're basically pulling data out of the data source by calling move next. And that's a typical for each loop, right? Whoops, a little too fast again. So that's a pool-based data acquisition model where you do a for each over a data source. However, that thing is very blocking, right? You're doing a for each, meaning you do move next to the next element, and if the element is not available yet, you're blocked there. You're just waiting for that thing to happen. That's not the thing you want to do with a stock exchange. You don't want to sit there and blocked, waiting for one stock exchange while the other one is happening. No, you want to react when data messages come in. So you want to be asynchronous, non-blocking, with regards to how you get to the data. And that's actually what we call reactive programming, where we have two abstractions, IObservable and IObserver, which are very much alike to IEnumerable and IEnumerator. And so the difference here is that data gets pushed at your application. You basically talk to that, say for example, again, the stock exchange, you say, dear stock exchange, when data becomes available, please call me back. And that's actually what the onNext message is for, and I will explain this in just a second. But so you basically set up a handshake that says, in the future, call me whenever data becomes available. You're not sitting there waiting for data to become available. You basically react to the data coming in. So it's basically an event sequence. So those are the two interfaces we have in Rx. Actually, those interfaces exist in the .NET 4 BCL, so you can actually find them in the system namespace. They're called IObservable and IObserver. So the contract is as follows. The subscribe method on IObservable takes in an IObserver. Think about it as follows. Say that you go to a bookstore or to a newspaper and you say, I want to subscribe to the newspaper. What do? Well, you basically send the newspaper that you want to receive editions of their newspaper in your letterbox. So the IObservable is your letterbox that basically will receive that data becomes available. The IObserver then has three methods. The first one is onNext. For the letterbox example, it would actually take in a newspaper of type, T would be newspaper. And you would actually, I somehow have automatic timing on this slide, that's not a good thing. But so it would basically get called when data becomes available. So you don't have to sit and wait there in front of your letterbox for the data to become available. You just have something that the postal office will just drop that newspaper in your letterbox at some point, and you can react to that. You might read it or just toss it away in the evening. You might also get an on error in your letterbox, basically saying, well, we're sad to announce you that the newspaper has shut down, because there was a bomb attack on, the printing office, like we can't send you those messages anymore. Like, that's unfortunate. And uncompleted means there was some graceful completion, which might be that the newsletter basically said, well, I'm not longer going to send you messages because, we sort of went bankrupt. It's not an exceptional event. Well, you could consider that to be exceptional as well, but, there are two ways of completion, right? Successful or non-successful. So, as you can see here, the whole observer now represents a callback. It's much like async callback continue with, but it has like three things on it, and the contract is slightly different because the onNext message can appear multiple times. If you have a task of T and you do continue with, the thing that's happening is that the continuation gets only executed once, because the task of T only computes a single value. It's an abstraction for single value computations. An IObservable is an abstraction for multi-value computations. When you subscribe to that thing, you will get multiple messages saying, like, here's the first newspaper, here's the second one, here's the first stock exchange message, here's the second one, here's the first mouse move, here's the second one, and so on and so on. So that's the idea of IObservable. So let's actually take a look at some queries. Let's just have some fun. I will just type all the code that's on the slide in the demo, which speaks much more than just some code over there. So the thing I want to do here is some UI programming. You can use it for many things. Everything that exposes events you can use Rx for to do those compositions on rich queries over data. So what I have here is just the WinForms app. I could use any UI framework, but I'm more comfortable using C# and JSON style to just new up some Windows form. I don't need any designer to do that. That's pretty nice. So I can do Ctrl F5 and just I have a form here with a text box and a list box. Pretty simple stuff. So that's my UI application. It has a fancy design. Now I want to start doing some stuff. Let's say I want to do text.textChanged plus equals, and I want to hook up an event handler. There are a couple of issues with that. First of all, how do I get to the text that has changed? Console.writeLine of e dot. The text is nowhere around. So .NET events, well, they are very great as signal wires to say something has happened, but they don't always carry on interesting information. So you need to start doing all sorts of transformations here, and you basically surrender to writing, imperative style code. You will do something like cast O to the text box and then do .text on that. So you already have a little piece of imperative code sitting here, even though like my text changed event could be seen as a sequence of data. Like, the first time it changed, the second time it changed, and so on. Now, if you have a sequence of data, there's something called link that can transform sequences using a projection. Why can't I just say, from events in text changed, select that ugly piece of code, and then I have an iObservable of strings. I basically want to transform every message into another message. Well, with Rx, you can actually do that. So let's actually show this. I can do something like this. I can import the event. In Rx, you actually have this type called observable, which lives in some namespace. And there we have some conversions from things like .NET events. So I'm importing text changed here as an iObservable sequence. This thing is of type iObservable of event pattern of event arcs. That contains all the info, but now we're in a world where we have rich composition. We have a lot of query operators on top of that. I can do something like text dot. I can do text.select, where, order by. Well, not order by, we don't have that in the asynchronous world. But you see a lot of those operations become available now for free on event sequences. So now I can write something like, access equals from t in text, select, and now I can dot into t.sender. I can still cast the sender to a text box, and I can return the text of the text box. Now what I have is I started with an iObservable of event arcs kind of things. Now I have an iObservable of strings. So I have done a simple transformation using a link query from event arcs into strings. That's pretty nifty. Now the way to listen to that is I do access.subscribe instead of access plus equals, because it's not a .NET event anymore. And now I can pass in, a callback. I can say, given every x, which is a text in the text box, console writeLine x. So this is a very simple event handler, but I didn't have to write the imperative code of casting things, inside some callback. I basically have lifted things out into the logic of a query expression. Let's execute this. Let's just type. It works. Now say I want to take this code and glue it together with web service calls. And every web service call for input, for example, to do a dictionary lookup, costs you $1. So say that I'm typing here reactive really fast. Well, as a user, I've basically issued 8 web service requests. How do you say, calm down, just go to the web service once if the user is not typing for 500 milliseconds? You can do that using .NET events. You just start a .NET timer somewhere and you wait for the timer to happen, and when the timer fires, you cancel something out, and oh my goodness, it's a lot of state maintenance to do that. Now in Rx, because we now have exposed the event as an iObservable, we have rich operators available that make it much easier to deal with this thing. We can say, hey, I have a text box. It produces strings. But don't tell me every freaking string that comes out of it. Just make sure that the user doesn't change anything for 500 milliseconds before you tell me. So you want to sort of slow down the event sequence. How do you do that? Well, in Rx you simply say .throttle. And you say time span from seconds 0.5. Now I have an IObservable of string. When I subscribe to it, I will only get messages, if the user didn't type anything within 500 milliseconds. So we basically throw away messages till the user has calmed down, is getting a piece of coffee or a cup of coffee, and at that point we send out the event. So let's execute this. I can type really fast, it's not coming out, I'm not going to a web service, but then I stop and after 500 milliseconds the event is forwarded. So now I can do all those rich compositions on top of those event sequences in Rx. Now another thing that I could do here, as a user I could be rather silly. I could change this with Bing and then type reactive. Well, I need to be much faster here. But say that I go to reactive, there it comes, I do backspace E, whoops, I got 2 reactive events after each other. The text hasn't changed, still it happens. Well, how do I filter out those duplicates? I can do that in Rx as well, because every duplicate will cause a web service call, and every web service call costs me money. How do I filter out duplicates with .NET events? Oh, you just keep some field somewhere and you have an equality compare and you just compare things against the last one and you assign stuff and you do all of this magic, which is you basically just write once and never read again. In Rx you can actually say, hey, if there are consecutive values that are the same, don't tell me about those consecutive duplicate values. I can say distinct until changed. Now we do all of that state maintenance for you. Now I have an IObservable that never can have 2 consecutive values that are the same. So I can start writing those rich query expressions on those event sequences. So now when I execute this, I can type reactive, takes 500 milliseconds. I can actually cancel out the E and place an E in the same place. The text hasn't changed, so Rx simply doesn't forward you the message anymore. It knows that it hasn't changed. So you can do all of those transformations on this stuff. Now to finish up, almost out of time here, to finish up I just want to go one step further. I've done all of this stuff already, the throttle and distinct, which I actually have sitting over here. This is the same code that I had prepared. The thing I want to do is do a little bit more. I want to go to a web service every time the user types a piece of text. So the user types something, a reactive for example, and then I want to launch an asynchronous web service call that gets the words that start with that prefix. So if the user types react, you get reactor, reactive, reactants, all of those things. So I want to do a very simple dictionary suggest over here. Something is a little out of whack here. Let's figure that out in just a moment. Oh, likely this thing. No incremental parsing. Cannot convert. We'll see that in just a moment, what that problem is. But so I still have the input sequence here, which is basically a sequence of text, a sequence of strings, which is throttled down and distincted so that you don't get a flood of messages. You basically scale down. Now I can write a query that says, for every term that the user writes in the text box, modulo all the logic I've done with throttling and distincting, please call a web service method called match that looks up in a dictionary called WordNet everything that starts prefix with the term that the user wrote. So now I'm basically for every entry in the text box, I'm going to a web service asynchronously and just that thing is going. And at some point it will forward the message and then that message will be bound to the UI thread. So that's the thing I'm basically doing here. I know what's going on with this. I don't know what's going on with that. That's kind of scary. Okay, I forgot something. What's words? Oh, words is not known. What's words? Dictionary word array. That should have worked. That's strange. Words. So like, I know. I need system.link. Good. So what I'm going to do here, after I compose, my text box over here, input, with web service calls, and I use some query operator in Rx called switch, that basically jumps from one sequence to the other. If the user types something new, we don't listen to the old web service request anymore, we switch to the new one. So we basically jump from one request to the other every time the user types. Ultimately, this thing returns an IObservable of word arrays. So every time the user writes something, a message appears on the output sequence, which are the word arrays that correspond with what the user is writing. If the user writes something new, and the web service call is going, and he writes something new again, basically, that switch operator will cancel out every previous call so that you only see the last value appearing on the screen. That's to avoid race conditions, essentially. So now that I have an observable of word arrays, I can subscribe to that thing. I will get the word arrays, and for every word array, I can basically, over here, clear the list box, and then take all the words from the word array that come from the web service and put them in the list box. And the way I do that is as follows. Every word array, dictionary word array, contains dictionary words, of course, and every such object which is generated by WCF, I have some web service proxy sitting here, actually contains both the dictionary in which the object was defined, or the text was defined, as well as the word itself. So I just want to get, the word out of that, because I'm not interested in the dictionary. It's always going to be WordNet. So what I'm doing in order to get the words out of that simple, array, I'm simply writing a link to objects query. From word in word, select word.word. It's kind of wordy, but, whatever. That's pretty simple code. It's just, link to objects. And so now what I have is, whenever I type something here, React, we basically issue a web service call that gets surfaced out using the IObservable sequence of word arrays. So to compose all those event sequences, the only thing I actually had to do was glue together, some observable sequences using query operators in Rx. So that's actually what Rx is all about. And you see there's a whole slew of those query operators. It's actually everything of link to objects, but now on event sequences, together with time-based operations as well. Like total is time-based, that doesn't make sense or that much sense for enumerable-based sequences. So to wrap up, Rx is about event processing. So here I have basically the breakdown of the whole landscape, I would say. You have asynchronous and synchronous computations. You have one-value computations and multiple-value computations. For the synchronous and asynchronous one-value case, we respectively have regular method calls, which I represent as func of t. That's you basically call something and you wait for that thing to complete. Or you have task of t. And now in the language you can deal with both of them. The first one we could always deal with. You can simply invoke something or call a property or whatever. Now we have await expressions to deal with asynchronous operations. So that's imperative style code. You sequence through statements with semicolons. You basically say do this, then do that, then do that, and the compiler might transform things for you in the case of asynchrony to lift it into lambda expressions. But you don't need to know anything about those callbacks. It just happens for you behind the await keyword. On the top, for multiple values, we have a single surface in the language, which is link. That's basically, from, select, where, all of that stuff. And it happens we can do that both on enumerable sequences and observable sequences, as you can see over there. So we can do both, pool-based iteration things, like link to SQL, link to entities, link to whatever that's based on IEnumerable of t. But we can now also, thanks to Rx, we can actually write queries over event streams of data. So basically, the asynchronous landscape boils down to if you do single value computations using task of t, await is a very nice abstraction for you. If you want to do event processing kind of things, you actually want to take a look at IObservable of t and the whole reactive extensions, which you can download from MSDN. So with that, as I said, asynchrony is everywhere. Windows Phone, Silverlight, JavaScript, you need to be asynchronous or you can't do anything. So with the C# stuff, you can now download the async CTP and use the await keyword, which makes it much easier to write this imperative-style asynchronous code with all your usual control flow mechanisms. If you want to do multi-value streams, event streams, and event stream processing, which is also asynchronous because you don't want to be blocked on events, you actually want to take a look, I believe, at reactive extensions. And you can actually ask me everything about that because I'm one of the developers on Rx nowadays. So with that, I would like to thank you for your extended attention because I've gone over a couple of minutes. Excuse me for that. I hope it was interesting. I will be around at the booth, so if you have any questions, please come to me and talk to me. Thank you.